Great, great, thanks. Yeah, I have quick housekeeping to go over. Yeah, so thank you first for the invitation to speak at this Flash Talks. And thanks to the organizers and also those who help with, I've written recording and pub quiz stuff. So hopefully that addresses everyone who I should be thanking. And yeah, the disclaimer is I won't be giving really any details for this talk, and try if I can do this, just refer you to this archive preprint number in the top left-hand corner. That's really where the details are hidden. And also, yes, there definitely seem to be 16 great speakers. I can definitely confirm 15 of the speakers are great. I can't really confirm about the last one, so we'll see over the next 10 minutes or 9 minutes whether that's true. Yeah, so what's going on? The setting is string algebras. So classically, these are finite dimensional algebras over a field, and I'm really focusing on some kind of generalization of them today over a local ring. And my talk is really just two examples. One is a string algebra over a local ring, and one is something that I think looks like a clannish algebra over a local ring. So not really a string algebra, but still in the same vein. So what's the setting? The setting is I start with a local noetherian ring R, and then you take the usual setting for classical string algebras. So I take a finite connected quiver Q and some ideal in the path algebra, but over R, so the path algebra RQ now instead of KQ for a field K. And then I take the quotient here. So lambda's always going to be this quotient. And the first example, the only example in this talk of a string algebra over a local ring is the two adic integers with the following quiver and following relations. So I firstly want to think about, imagine if I replaced the two adic integers, say with, let me suppose I took R to be the power series algebra in one variable T. I just imagine this as a replacement for the moment. And in that case, I imagine if I replaced 2 with this variable T, if I did that, then what I'd end up with is what Charlotte Ricker called a completed string algebra. So you'd really be looking at the completed path algebra with these quadratic relations, and so that would be really a completed string algebra. And Charlotte Ricker looked at that case and classified the finitely generated modules for such a thing. But if I erase all that and go back to the case I was thinking about, so the setting I'm taking here is the two adic integers, this quiver with a 2 cycle and loops at either vertex, these quadratic relations, and then these relations here really make this algebra lambda module finite over R. And so you really at least have something that's would usually be, say, finite dimensional or finitely generated over a power series ring, or yeah. And this is quite a nice example because finitely generated modules over this ring correspond to so-called quadratic functors, and quadratic functors arise in topology. It's explicitly the topology of Moore spaces, and this topological connection was really studied by Baues, at least in the early 90s. And the classification of finitely generated modules over this algebra was solved by Drozd. And Drozd gave some more properties about projective resolutions of the finitely generated modules. So I think that's quite a nice example. And in this preprint, I was looking at really the notion of an admissible ideal, because usually when you have a string algebra, you're killing out by an admissible ideal, and I wanted to understand what an admissible ideal would be in that setting. So what's an admissible ideal? If I start by looking at, I'll just give you some notation. So A subscript I J, this this notation here, that's going to be the R span of the length L paths where L runs from I to J. An MQ, that's going to be all elements in the path algebra, but where the scalars, the coefficients of your paths, all come from the maximal ideal M in the local ring. Yeah, so this would be all elements in your path algebra where the coefficients were divisible by 2. So yeah. Then what does it mean to be admissible? So this is in terminology of Raggi-Cardenas and Salmeron from quite old work, but seems old now, 1987. So an ideal is admissible if the following conditions are holding. So bounded should be bounded above and bounded below. So what's bounded above? Bounded above is where your ideal you're claiming is admissible, is contained in something. So it should be contained in, say, this M span plus the arrow ideal. That's just all the paths of length at least 1. And if you just think about the class, and then the other condition is that when you intersect that with all the paths of length of at least 1, it should be contained in this sum. So that's the paths of length at least 2, and this is the elements which involve no length 0 paths and where the other coefficients come from the maximal ideal. And it's quite a confusing condition, but if you just consider the classical setting where you're looking at a field and take M to be 0, this is just saying that I is contained in rad squared of the path algebra, the arrow ideal squared. So it's a bit more familiar if you let M equals 0. And bounded below is really the analog of where some power of the arrow ideal is contained in I. But you need to adjust for having a possibly non-zero maximal ideal here and here. Yeah, so this condition that I'm highlighting now says nothing, and the one above really tells you this. And we can revisit the example, and there's some calculations that slowly convince you that the example 1 above really was an admissible ideal. Yeah, so for example, you can take k equal to 3 and n equal to 2, and this bounded below definition would be satisfied. I'm running slightly over time, so I'll just move on to the clannish example. And this is a much more complicated example, and I won't go over the details. But this comes from work of Roggenkamp from 1980. And Roggenkamp looked at this algebra here. So this is a subring of the product of these rings. So this is really something called a Beckstrom order. And these identifications are where you look at the subring such that the coefficient here and here are the same modulo 11. Yeah, so the local ring we're looking at here is the 11 adic integers. And this should be somewhat reminiscent of the Brouwer tree of the Matheiu 11 group. Yeah, so this is something that I'd consider somehow an example of a clannish algebra over Z11. So it should be tame, and I'm currently trying to think about how one could show it's tame using the functorial filtrations method. And if I just jump back to example 1 again, this is what I was saying at the beginning. So here this is the first example over the 2 adic integers. You can see lambda is a subring of this product. So again, this is some kind of Beckstrom order. And as I said, finitely generated modules correspond to so-called quadratic functors, which is important things that are arising in topology. But this example, if we just look at the relations, aside from these kind of quite weird things that are adjusting for this generalization, these are gentle relations. These are quadratic relations, and they really make this look like a gentle algebra. And this is the theorem of the talk. Because you can see this is a gentle algebra over Z2. This ring is both Ewanager-Gorenstein, and from results in my PhD thesis, you can see this thing is derived tame in a general sense. Yeah, so that I'll leave it there for now. Yeah, thank you.